So we're going to discuss something called a binomial random variable and calculate binomial probabilities along the way. But to try and understand this, what we're going to do is we're going to start with this kind of a question. Suppose that you're going to take a quick SAT type test and that each question has 5 choices with only one right answer. Let's find the probability of getting 2 wrong answers and 4 correct answers. Maybe this is the threshold for you to get accepted someplace or pass the exam, etc. So we want to calculate that probability. So one way that could happen would be probability of getting a wrong one, another wrong one, and then 4 correct ones. So because these are independent, I mean, what you guess on the first one is not going to increase your odds of guessing correctly on the second one. I can treat this as a product of probabilities. So, okay. And now let's start thinking about what the probability is that somebody guessed wrong on this. So what's the probability of a wrong guess? Or you can do what's the probability of a correct guess. Either way.
The probability of a wrong guess would be 4/5, and correct would be 1/5.
Good. Those are the 2 things that can happen. Notice that they total up to 1. Okay, so that's all that can happen. So these probabilities would be, let's see, 4 out of 5 times 4 out of 5, and then 1 out of 5 times 1 out of 5, etc. So your choices, or the probability of getting the first 2 right and the 4 wrong, like that would be 16/5 to the 6th. And I think it's what, 15,625, something like that. Somebody help me out because I was never very good at math. Kind of small, right? Not sure you can guess by or count on guessing your way through, but this doesn't really give you the whole story because there's different ways that you could have 2 correct or 2 wrong guesses and 4 correct guesses. Now the one I outlined is right here, but you could guess wrong, correct, and then wrong, and then 3 correct, or something like this, and so on. So there's a lot of different ways that you can arrange these different outcomes. So the question then becomes like, well, how many different ways are there that I can have 2 wrong guesses and 4 correct guesses? And one way to calculate that is to ask yourself, how many ways are there to choose 4 correct guesses out of 6 trials? Yes.
I'm kind of confused. How did you get 4 out of 5 and then you said 1 out of 5?
So the probability of a wrong one, probability of a correct one?
Yeah.
Sure. There's 5 choices. So you're answering your question, you've got 5 choices, right? How many of them are the correct choice? How many? No, there's only 1 right choice. So that's your probability of guessing correctly, is that there's 1 out of 5. Now the probability of guessing wrong is the opposite of that. If there's 1 right guess, there's how many incorrect guesses or wrong guesses? How many ways are there you can guess the wrong answer?
4.
4. So that would give you your 4 out of 5 there. Does that help out?
Yeah, a little.
Well, let's do it this way. Wrong, correct, wrong, wrong, wrong. So this is an example of your sample space, right? There's one correct guess out of 5 possibilities. So the probability that you get that out of these 5 guesses, so n equals 5, here, the probability that you guess correctly is that 1 out of the 5. The probability that you gets wrong, well, there's 4 of those. So probability of correct is 1 out of 5. Probability of wrong is 4 out of 5. It's just a numbers game. That C can be anywhere here, it doesn't matter. It's not going to change these probabilities. You have 1 correct out of 5, and there's 4 that are wrong guesses, again, out of that 5. Is that a little bit better?
Yes, thank you.
Mm-hmm. So I put those together to find the probability that you got exactly the first 2 wrong and the next 4 right. And it's just going to be a product of these probabilities because of the independence of these events. But that kind of understates things. There's a lot of different ways that you could have 2 wrong guesses and 4 correct guesses. Now, if you're trying to pass this test, does it matter to you if you got the first 2 wrong, or the middle 2 wrong, or the last 2 wrong, or some other combination?
No.
Nope.
No. What matters is not where they got them wrong, but that you got them wrong. So what we want to do is we want to understand how many different ways are there that I can choose 4 correct guesses, and by default that means two wrong guesses out of the six trials that I have, or the 6 questions that I have. So it's this one right down here. I need to count how many ways are there to choose 4 correct guesses out of 6 trials. Now, we did some counting stuff on section 4.4. So what's that going to tell us? Am I going to use a factorial for this? No, because factorial would just list how many ways I can calculate, or how many orderings there are of, say, 6 trials. So that's not it. What else did I have in that section that could help me out? There was permutations and combinations. Which one do you think I want here?
Combinations.
Alex says combinations. Should I do combinations or permutations? What do you guys think?
Combination.
Combinations, because the order doesn't matter, right? So it's going to be 6, choose 4. And you should take out your favorite calculating device, either Google Sheets or your graphing calculator, and remind yourself what 6, choose 4 gives you. Let's tell you. What's 6, choose 4 going to give me?
15.
All right, 15. Thank you. Now, if I wanted to actually calculate this probability, I got to take the probability that I have here and really multiply it by 15, because there's a lot of different ways that this can happen. There's actually 15 different ways. So the probability of 2 right, or excuse me, 2 wrong and 4 correct is really 15 times 16 over 15,625. So it'd be a total of 240 over 15,625. So that would be the correct probability. Now this whole thing is an example of something called a binomial random variable. Binomial random variable. Okay, let's check out what those are. Something is a binomial random variable if it fits. X has a binomial distribution if it fits. Now, fits is not an arbitrary choice here on my part. It actually represents something. So let's look through what fits represents. First is F. You have a fixed number of trials. Next is I. These trials are independent. After that is T. There's exactly two outcomes in each trial, typically success and failure. And last but not least, there's the same probability of success throughout the trial. Same probability of success throughout the trial. Or experiment throughout your N trials. You're going to repeat this N times, and that's going to result in a binomial random variable. So X for us is the number of successes. So if X is the number of successes in this fixed number of trials, then it's a binomial random variable, assuming that the rest of these qualities are met. Now, I'm going to give you some notation for this, and it's not the prettiest notation, but don't distress because we're not actually going to have to worry about calculating this stuff by hand. There's a lot of help for us here. So can I move this? I'm good there?
Yeah.
Yeah.
Thank you. So let me discuss the notation here. If X is a random variable or a binomial random variable, I'm going to stipulate that as NP with N trials and probability of success equals P. Let's make this a little bit clearer. There we go. Then probability of X is given this way. And choose X times probability of X, 1 minus probability of success, and N minus X. And I'll help interpret all these different terms for you. X is the number of successes. P is a probability of success. And 1 minus P is a probability of failure. So we can apply this to our current example. Let's see what probability pops out of that. So for the current example, we had 6 trials and probability of success was 1 out of 5. Mhm. All right, so let's take a look. Probability of exactly 4 successes is going to look like this. 6 choose 4 times 1/5. It should be 4/5. No, it should be 1/5. That's right. First time, 1/5. To the 4th power times 4/5 to the 2nd power. So that's the probability that we just calculated. And that'll be 15 times 1/5 to the 4th power times 4/5 to the 2nd power. So 240 over 15,625. So not necessarily the most pleasant calculation, especially if you have to take the time out on your calculator to get this. Excuse me, but there is help on the way. So let's take a look at how to do this on some of our technology. And there's 2 different methods that I'm going to show you. Now, a lot of times in the homework, there'll be a button that you can press and it'll give you a table just showing you all these different probabilities. And you can answer questions based on the table. But I'm going to show you how to generate your own tables and do a lot more. Let's start with the graphing calculator. I'm not going to use this much today, but I will show you how to use it here once. So let me clear out all these things. Now on the graphing calculator, you can get to what you need to by going to distributions, which is right above the vars key. So to get there, you can hit the 2nd key and the vars key, and you'll see a key history below here so that you can try and follow what I've done here if you need to afterwards. Now I've got to go to the next page because my choice isn't on this page. And I think I'm just going to go with the up arrow.
Quick question. Where's the bars key?
Vars key.
Oh, vars.
It's right underneath the little down arrow. So if you hit the
Oh,
second
vars. Okay. Sorry.
vars,
Second distribution vars, and then it's
then you go up 7 times. That's what the little 7 here represents. You go up 7 times. Now there's 2 choices. There's binomial PDF and binomial CDF. So we want binomial PDF. Now the form of this command, if you don't have a TI-84, the form of this command for your TI-84 is this: binomial PDF, and then you're going to want to type in N, and then P, and then X. And that'll give you the correct answer, the number of successes out of, or probability of this many successes with this probability of success out of N trials. So let's see if we can't match this number here. And in fact, afterwards, we'll go back and calculate this. For right now, right here, I want to press the Enter key. And it's a menu-driven thing. You'll type in a 6, and then you type in the probability. You can type in 1 divided by 5 like I did, or you can type in 0.2. That works as well. we want a total of 4 successes. So you press enter here, and then you press enter a couple more times because the first one's going to paste this into your home screen. So if I do that, now paste this into the home screen, and I should get this. Let's compare that to 240 divided by 15,625. And they're identical. Cool. Nice. So for those of you with a graphing calculator, were you able to get it this way?
I have a
Yes.
graphing calculator, and when I click that, it doesn't bring up like the format. Like mine's just an empty parentheses for
Yeah.
binomial PDF.
Right. So if yours is just an empty parentheses, then you just got to type in the numbers. So you got to type them in yourself, like what I have up here. It's just not menu driven like everyone else.
Right. You
But-
just use the commas then.
Yeah, use the comma above the
All right.
number 7. So type in a 6, comma 1/5, comma 4, and you should still get the 0.01536.
Right. Yeah. Thank you.
Hey, appreciate the question. Thank you. Now, if you don't have a graphing calculator, or if you don't have one like mine and you don't feel like taking out the manual, another possibility for you would be to do this. Now, I'm just going to choose kind of a random cell here in my Google Sheets. And of course, all your Google Sheets commands start out with an equals. And now the format of this command is actually in the handout that I sent you yesterday. Should be at the very bottom. So on Google Sheets, you want to type in binom dis, D-I-S-T, and then X, number of successes, and then N, and then P, and then false. Now it says cumulative. I'll have to explain that in a little bit. But for right now, the general format of your command should be like this. So for this current example, it's going to look like binom distribution 4, 6, 0.2, false. And I should get that 0.0 whatever number 3 something that we got just a minute ago. So let me go back here. Binom distribution. And as soon as it recognizes, I'm in the habit of pressing the enter key because it puts in the left parenthesis for me. And I know I got it right. So 4, 6, 0.2, which is 1/5, false. So one more time on that. Let me highlight this. You can see the command up here. There you go. Are you able to get this one way or another? Did that match the calculation I have here on the calculator?
I don't,
Yeah.
It did?
Same one.
Just
Okay,
pick a
good.
different
Yeah.
order.
For a second, I was thinking it didn't match, but I thought I was wrong, but I was merely mistaken. So we're okay there. All right. Are you able to get that number either out of Google Sheets or out of your graphing calculator? You have to be able to get it one way or another. It doesn't matter to me which way you choose.
Yeah,
Okay. No one's left behind. That's what everyone's telling me. You can get it one way or another.
I'm a little confused on how to get it on the graphing calculator, but I understand how to get it from Google Sheets.
Okay. You can look back. I'm mostly going to do it on Google Sheets because Google Sheets is going to offer some advantages. But let me give you one last glance at all the calculations that I did here. So I started out by clearing the home screen, and then I pressed all these buttons. The little number here represents, for instance, you got to up arrow 7 times. All right. but mostly you're going to be looking for it under distributions. So let me just run through it once again. You know, actually, I'll tell you what, I'll try and do another one off the graphing calculator in a little bit. Right now, what I want to practice is practice identifying whether or not we have a binomial random variable. So for that, I want to go back, I want to go to the homework. And let me just find the right page here. It's going to be page 209. So let me go to page 209 in the book. And the idea here is we're just going to identify whether or not something is or is not a binomial random variable. So in doing that, what we have to do is we have to decide if it fits. So let's take a look at the first one. So this is homework page 209. Clinical trial of Y-sort. The Y-sort method of gender selection developed by the Genetics and IVF Institute was designed to increase the likelihood that a baby will be a boy. When 291 couples use the Y-sort method and give birth to 291 babies, the genders of the babies are recorded. So what we want to do is we want to decide, does this fit? So do we have a fixed number of outcomes or a fixed number of trials? Let me look back at the problem. Is there a fixed number of trials here? Ah, what happened? All right, don't make Alex do all the work here. Someone help him out. Is there a fixed number of trials here? And it'd help out if I had a problem up there. There you go.
Yeah.
Yeah, there's 291.
Yeah.
Are there two, or excuse me, are the outcomes independent? If somebody
Yeah, they
as a boy, does that affect the probability someone else has a boy?
no.
No.
They're independent. So cool. We got independence. Thank you, Molly and Alex. Someone else here. Are there two outcomes?
Yes.
Yeah, I hope so. Boy and a girl, right?
Work.
All right, so boy and a girl. And finally, probability of a baby being born a boy or a girl, whichever way you want to think about it, that's going to be the same throughout the trial. Not like as you go on, you're more and more likely to have a boy or more and more likely to have a girl. That probability is going to stay the same throughout the trial. So this is a binomial random variable. Hey. So it matches all four of those different criteria. Fixed number of trials, independent trials, same probability of success throughout the trial. So it fits. Let's try problem number 7. In a U.S. cellular survey of 500 smartphone users, subjects are asked if the abbreviations such as LOL, BFF are annoying. Each response was recorded as yes or other. So let's run through this. Maybe get some more help from some different people here now. Is there a fixed number of trials?
Yes.
Yes. Are the trials independent, assuming you're choosing these people at random?
Yes.
Yeah. What you think or what somebody else thinks, yeah, those are going to be independent. So 2 down, 2 to go. Cool. 2 outcomes.
Yes.
Yes.
Yep. 2 outcomes, either yes or other. And the same probability of success throughout the trial. But this one gets a little sticky, all right? Because typically when you sample with without replacement, what happens?
The number.
Say again?
The number changes.
Yeah, so those probabilities change. So if you remember, sampling without replacement leads to dependent events. And what that means is that the probability of success changes from one trial to the next. But at the same time, we have the 5% rule. 5% rule can come to our rescue. And what that said is if your sample is less than 5% of the population, you can treat the sample as independent events. Or you can treat the events as independent. So even though they're not independent, you can kind of treat them that way. And that makes a world of difference. It makes your calculations a lot easier. In some cases, it might not even be possible to do it the other way. Now, kind of a little trick that I've come up with to help you out with the 5% rule is this. If you multiply your sample size by 20, your population size should be greater than that number, and then you can use a 5% rule. So here we go. Multiply your sample size by 20. If your population size is greater than this number, you can use the 5% rule.
Which number are you referring to? When you say greater than this number?
Greater
Are you referring
than
to 20 or the population multiplied by 20?
the product of your sample size and 20. So sample size times 20. So if your population is greater than sample size times 20. Thanks, Joe.
Yeah, thank you.
So that's what you're looking for. Population is greater than the sample size times 20, then you can use the 5% rule. All right, so let's go back up to problem number 7 then. We want to decide, can we use, or are the probabilities the same? And the question comes down to, well, can we use the 5% rule? Well, let's think. That'd be 20 times 500, that's 10,000. Is it likely that there are more than 10,000 smartphone users out there that you could sample from?
Yes.
Yeah, I'm thinking that's a good chance. In fact, there might be more than that in Oakland County. All right, so the answer to this last one is, yeah, we can treat those as being the same. And this is a binomial random variable. Is a binomial random variable. Nice. Let's do another one like this. Problem number 8, I think. Maybe 2 more like this. How about problem number 8? 8, we'll do 8 and 9. So same kind of thing, same setup. We have 500 smartphone users are in this survey. They're asked to comment on these abbreviations, LOL, BFF, and each response is recorded as yes, no, or not sure. Well, let's work our way through here. Do we have a fixed number of trials?
Yes.
Yes. All right, so we got that. Are the trials independent?
Yeah.
I mean,
Yes. What somebody thinks about these are independent of what you think about them, assuming that you're choosing these people at random. 2 outcomes?
No, aren't there 3 for this one?
Yes.
Yep. Fail. Yeah, there's 3 outcomes. So this is not a binomial random variable. Binomial random variables can only have 2 outcomes. Fails. So it's not a binomial random variable. Last one like this would be problem number 9. Any comments or thoughts on problem number 8? All right, so we're going to run through this thing again for problem number 9. The members of the Senate in the 113th Congress included 80 males and 20 females. 40 different senators are randomly selected without replacement, and the gender of each senator is recorded. So let's run through this one and see if it's a binomial random variable. Do we have a fixed number of trials?
Yes.
yep.
Are they independent?
Yes.
No.
Well, we're sampling without replacement, so that necessarily leads to dependent events, but can we use the 5% rule? It's a good question. Can we use the 5% rule? Well, is our sample size times 20, is that less than the population size? What was our sample size?
No. 113 senators.
That'd be the 113th Congress, but our sample size was, I believe, 40, right?
Yes.
Yeah, so it's not jumping out in your face, but there it is. 40 different senators are randomly selected without replacement. And that's important that they're selected without replacement, because that's telling you that these are going to be dependent events unless you can use the 5% rule. Can we use the 5% rule?
No.
20 times 40 is 800. How many senators do we have?
40.
No, how many senators are there?
In the total
13.
population.
Total population of senators?
100.
100. So can I use a 5% rule?
No.
No.
No, I can't. If I can't use a 5% rule, then guess what? These are no longer independent, and that's it. I don't even have to look at anything else. Doesn't matter that they're male or female, that it satisfies 2 out of the 4 or whatever. Fails one, it fails altogether. So this is not a binomial random variable. Not a binomial random variable. Well, where we do have binomial random variables, we're in good shape. We can calculate probabilities, etc. But first, you need to understand where these happen. This would be a good test type question. You know, I'll give you a series of descriptions like I just did and say, are these binomial random variables? You have to pay attention to the 5% rule though, because if you're sampling, then you want to make sure that your samples can be treated as independent, even though they might not exactly be independent. Questions on that before I move on to some actual calculations from some of the examples that we have in our homework? These should be on the handouts that you were given. I'm going to start with a very simple one. Now, you can answer these probabilities by clicking on this and getting a table and just looking at the table to answer your probability questions. But this is the 21st century. We're going to do things a little bit more fancy than looking up in tables. Tables used to be the way that people had to do these things. In fact, in some countries, they still use tables like this stuff to calculate probabilities. And there's one in here someplace for binomial probabilities. It's in the back of your book. So not sure which one it is, but there's tons of these tables. And I talked to the author one time and he's like, yeah, I keep this in the book because it gets shipped to some countries that don't have access to technology. And there's some professors that are kind of set in their ways, would be a nice polite way to say it. Okay, we're going to do this on Google Sheets. Assume that the procedure yields a binomial distribution with n equals 3 trials and a probability of success of 0.3. Use the binomial probability table to find the probability that the number of successes is exactly 1. Well, let's do our own version of this. So this is example A. So n was equal to 3, probability of success was 0.3, and I want x equal 1. We'll do a little bit better than that. We'll start out with x equal 1. So let's go over to Google Sheets. And let's see. All right. So I'm just going to come down here to a random cell. Actually, I want a whole bunch of cells. Now, if we have n equals 3 trials, what are the possible number of successes we could have amongst those 3 trials? Certainly, we could have 1 success. What are the different possibilities that we could have there? Could I have 2 successes?
Yeah, 0, 1, 2, or 3.
Perfect. Thank you, Joe. This is exactly what I was looking for. So 0, 1, 2, or 3. I'm going to put those all in little columns. But what I'm going to do is I'm going to get a nice table of all these probabilities. Now, the question's really only asking for this one probability, but let's do them all. All right. This is the table that you would see if this was a live link that I could click and figure out, what the probabilities were for that, just based on this table. As before, we're going to type in equals and then binom. As soon as you get to the D, just press the Enter key for binomial distribution. Then we got to type out the rest of the command. Now, the first thing I want to do is I want to click this cell. Now, there's a 0 in there, so this is going to be the probability of 0 successes. Now the format of this command is the next thing that I want is the number of trials. So that'd be 3. The probability of success. So we need a comma, 0.3. And then I've been telling you that I want to type in false. So you should get something exactly like that. Let me highlight this again so that you can see this. So on this one, you click equals binomial distribution. You want to click this cell, the one that has a 0 in it, comma 3, comma 0.3, comma false. Now the nice thing, once you've got this done, is that you only have to do it once. You can just drag this down and you get all these probabilities for everything. So in particular, probability that x equal 1, which is what this problem was asking, is 0.441. Okay. Now where I'm concerned about it, I'll tell you I want this many decimal places. By the way, quick review problem from our previous work. What should this total up to if I added up all 4 of these probabilities?
1.
1.
Should total up to 1. If it's a probability distribution, it has to have numerical values here and should total up to 1 here. And it does. Cool. So there's example A. Yay. Are you able to follow that? Able to keep up with that?
Yes.
Can you show us how to do that on the calculator?
The problem with doing it on the calculator is that you kind of have to do it one at a time. There is a little bit of a trick that I'll show you with this next problem. So on the calculator, let me clear out all this stuff and clear this. All right, so we're gonna go to the distribution key. So you're gonna hit second and then the vars key. Now that's right underneath the down arrow to the left of the clear key. And then I wanna go up 7 times and that'll take me to binomial PDF. Binomial PDF, comma, trials now is going to be n equals 3. Probability of success was 0.3. And I wanted exactly 1 success. And then I'll paste that in and press enter. Now, if you have an older calculator that doesn't give you this menu thing, you can just type in the command just like what we did here, except put commas in yourself with the key right above the 7. So there you go. Same thing, 0.441.
I'm sorry,
Thank you.
is the 0.3, was that obtained by, like only
That was given to you.
one? Okay, oh, it was, okay, yeah. Never
That's
mind then.
right there.
Well, there we go, thank you.
No problem. Okay. The challenge comes when they ask you for something like they do in part B here. It says, assume that random guesses are made for 8 multiple choice questions on an SAT exam so that there are n equals 8 trials, each with a probability of success given by 0.4. So that's a little strange, but we're going to go with it. Find the probability that the number of correct answers, x, is fewer than 4. So, okay, let's convince ourselves that this is a binomial random variable. That is the number of correct answers. We've got a fixed number of trials, yes. Are they independent? Well, if you're guessing right on one doesn't help you guess right on the next, so they're independent. 2 outcomes, you guess correct or not, and the same probability of success. Probability is 0.4 all the way through. So that's perfect. So let's write down some of the relevant information here. So we got that n equals 8. P is 0.4. And I want to find the probability that x, is it less than or less than or equal to 4? Which one do I want there? Should I put a less than or equal to or a less than? Let's look back at the problem. Do I need to include an equal to with my probability?
No,
No.
just less than.
Just a less
Just
than.
less than. So when I calculate all these probabilities, I don't need to calculate what happens at 4. Basically, I need to calculate all of these, and I need to add them up. So it's going to be the probability that x equals 0 plus probability that x equals 1, 2, and 3. And so let's look back at Google Sheets and take a look at things there. So I'm just going to continue with this example and type in numbers like this. I want to go all the way down to 8. So let me just extend my table a little bit. I don't need 9. I'm going to mash over these possibilities here. So I've got the numbers 0 through 8. And then I got to recalculate these probabilities. So I'm assuming you got these numbers here now. Let me edit this command a little bit. In fact, I'll just start all over. Equals binomial distribution. So binomial distribution, press the enter key. Select this one, that's your x. That's the number of successes, comma. Now, how many trials did I have for this particular problem? What's n?
Points.
That's
Oh,
probability.
It was 8.
yeah.
8. So there's 8 trials. Probability of success was 0.4. Boy, that'd change a lot of lives if the probability of getting a right answer on the SAT was 0.4. Comma, remember what comes after that one, the probability? What's part of the command?
False.
False. So that's what your first cell should look like. You want to get this one right because the rest of these are just going to be copied from that first one. So if you make an error here, that's one thing computers are great on is replicating errors. you're gonna get an error 8 more times.
Mhm.
So
Wait,
we're good with that one. Can I press the enter key here?
wait. So that was the binomial distribution.
Binomial distribution, and then
The
the
0.
cell to the left. Yeah.
Okay. So
So you don't want to type in the 0. You want to type in the cell to the left.
okay.
And then 8. So comma 8, comma 0.4, comma false.
Comma 8, comma 0.4. All right, comma 8.
And it should give you this probability. Does anyone know what's going to come next? You're going to drag this cell, starting with that square in the lower right-hand corner. You're going to drag that calculation all the way down to fill out the rest of your table. Yay. So
Okay.
are you able to get these probabilities here?
Yeah.
Now
Got it.
leave a column blank because we're going to go back and fill this in a little bit. But right down here on this line here, line 3, let's calculate the probability that they're asking for in this problem. Now that probability is really the probability that x equals 0, or x equals 1, or x equals 2, or x equals 3. what do I need to do to get that probability?
Add them up.
Add them up. Thank you, Joseph. So it's going to equal the sum, parenthesis, and then click and drag, sum of these probabilities. Now, hopefully you left yourself a column of space in there. I put that one right there. All right. So the answer to this question is simply 0.594.
I didn't get that. I got 1.
Does your probabilities match what we have here, Jaleisha? Do probabilities match you? Now, it's an interesting question. If you added them up at the bottom, if I add up sum of all of these, I should get exactly 1. And I do. But this one is just the sum of those first 4 probabilities. And it should be a little bit less than 0.59 or a little bit less than 0.6.
That's where I messed up at. I added them all up. I'm sorry.
That's okay. No, it's all right. It's a good teachable moment. So cool. Are we okay here? All right. So we calculated this problem by just directly summing up these things. But there's a different way we can approach this. And that's why I asked you to leave this extra column here. So what I want you to do with this extra column is first start by typing in an equals. And then we're going to go back to our binomial distribution. Binom dist. And just like before, we're going to click here, because that's the number of successes we're interested in, comma 8, which is the number of trials, comma 0.4, which was the number of successes. But in the first iteration of this process, we did false. Now let's try typing in true and see what change that makes. And for this first cell, it's identical to what we just calculated. And you're like, well, big deal, it didn't do anything. But wait, there's more. If you take this calculation and drag it down, you'll see that the numbers do start to get different. Well, wait a minute, that second cell doesn't match, that third cell doesn't match, and so on. So what are they doing in column C that's different than column B? Can anyone figure that out?
The fourth variable that you put into binom dist is cumulative, and if you set it to true, then it accumulates the values before it, so you don't have to add it manually.
That was perfect. That was absolutely spot on. Thank you, Lydia. So what it's doing for us here is it's doing the probability of anything less than or equal to 1, or the probability of anything less than or equal to 2. And if you take a look here, this is the probability that x is less than or equal to 3. And that probability exactly matches what we calculated just a minute ago when we added all those up. So if you click there, you can see what we did. We added those up. And that's exactly what binomial PDF, or what binomial distribution is doing for you if you hit true is the option. So kind of back over here, you can do that same kind of thing if we hit binomial CDF, that is cumulative distribution function, as opposed to probability distribution function. So quick look at that. Let me go up to binomial CDF instead of PDF. And we'll see, 8 trials, probability of success was 0.4. X value is 3. Enter, enter, enter. And it's giving me the exact same thing that I would get if I did it with Google Sheets. So there's a couple ways you can do that. And this binomial CDF problem or function is really helpful. There's some problems that become much easier to do with this than without it. So just take note of the difference there.
All right. So I know, Lydia already discussed it, but so basically for this, all of the probabilities, instead of being counted as, separate, they were cumulatively added up to that one point. Is that?
Yep.
Is
That's
that
exactly
okay.
that's exactly what's going on. And you can
Okay.
see it here
Mhm.
because this probability matches this one.
Okay.
You know, we can
All
see
right.
it in one other place. I think Jaleisha added everything up down here, but guess what? Right over here, this is the probability that x is less than or equal to 8. And that's the probability of all of these things added up, and it's exactly 1. So
Okay.
beautiful. It's exactly 1 either way. So nice. Got that one. So we've got something else that we can work with now in terms of calculating our probabilities. Let me share some more stuff with you about a binomial distribution. Mhm. So in our next video, we're going to talk about the mean and standard deviation of a binomial random variable. So like and follow.